So even though you did not do this problem for homework last night, we're kind of getting down to the nitty-gritty. And in looking at some things, there was a few items that we hadn't covered, and so I wanted to make sure I didn't skip any things. And this one had one of the items that we had kind of glazed over and not necessarily covered. So the topic that this one covers that we had missed and hadn't really gone over so far is combining means and combining more than one mean and more than one standard deviation. I don't think that has an apostrophe. So combining several means and at least two means and at least two standard deviations. Okay, just adding and subtracting them and doing those together. And the bottom line is that your means will, so the means add and subtract like you would normally think them to. So the means do add and subtract regularly. But the standard deviations, if you are combining two standard deviations or subtracting two standard deviations, for combining standard deviations, you have to go through what's called the Pythagorean theorem of statistics. And we've done that before, and so you'll recognize it when you see it here shortly. But remember, you would do the square root of one of the standard deviations squared plus another standard deviation squared, and then you would take that square root of that. Okay. So this free response is a good one to go through because it covers that and a couple other things. All right, so that's why I wanted to do it together with you, even though you had not done it. So let's take a look at it. Here we go. So flooding has washed out one of the tracks on the Snake Gulch Road Railway. This one right here. So that track is not usable. The railroad has two parallel tracks from Bull's Snake to Copperhead, but only one usable track from Copperhead to Diamondback. So only one usable track here, even though there are parallel tracks in this section here. Until it is repaired, the washed out track will remain unusable. If the train leaving Bull Snake, so let's call this the X train, if the X train is going this way and arrives at Copperhead before this train, the Diamondback train, we'll call that the Y train, gets there. So the X train is coming along the track to Copperhead. It gets there and the Diamondback train is in the way. What's it going to have to do? The X train is going to have to wait until the Diamondback train gets there and then moves on to this lower track and moves on out of the way. Okay, so that's the storyline of what's happening first, or happening here. So we then have the average and the standard deviation for their times. So we know how fast they're going, and we're interested in all those kinds of things related to that. So let's go here. Every day at noon, a train leaves Bull Snake and heads for Diamondback, and another leaves Diamondback, heads for Bull Snake. So assume that the length of time for train X is normally distributed with a mean of 170 and a standard deviation of 20. So let's write that down here. So this train X averages 170 minutes to get to Copperhead and a standard deviation of 20 minutes to get to Copperhead. Okay, assume that the length of time Y, this train over here, the average time for this train is actually longer. It takes 200 minutes for whatever reason, terrain, whatever. And the standard deviation, though, is less varied, and it's only 10. Okay, so those are the facts. That's the storyline. That's what's going on. So these two trains aren't independent of each other. So whatever one is doing, it's not affecting this mean and standard deviation of the other. So let's take a look at the first question. The first question says, what is the distribution of y minus x? So when I had even done mine, I kind of missed out on the fact that that essentially is asking you to describe the distribution. So what things does it want you to include? Shape and outlier, center and spread. Now, because we do not have regular data, the outlier will be out of range, and we're not dealing with the outlier. But we do need to talk about the shape. So what will the shape of the distribution, if we got both of the individual ones are normally shaped, what do you think of the distribution of y minus x will be? Yep, so the shape is going to be normal shape. Okay, now, for you people, AP testing, I want to warn you, you cannot just willy-nilly throw around that word normally shaped. We can specifically use that here because they had used they had used that in their description of x and y. So that clears us to use it. Otherwise, when you are describing shape, you should be using words like unimodal, symmetric, skewed left, skewed right, those kinds of things, unimodal and symmetric. If you don't know it's normal, then you're not clear to say that. You need to describe it as unimodal and symmetric, okay? I don't know if one's normal and skewed what you would say, so hopefully that, I don't imagine that would happen, or if they did, they would give you some way to figure out what's going on. Okay? All right, so now, center, what would we be dealing with? What center would we use to describe this problem? Mean. Center, mean, median, mode, the mean we're going to use. So we're going to say that the mean of y minus x, that's what we're trying to get. The mean of y minus x. So what do you think that is? It is 30. Because do you see that? 200 minus 170. So the 200 from y minus 170 for x is, on average, 30 minutes longer when you take y minus the x. Okay. Shape and outlier, center, and spread. So what spread will we be using? IQR, standard deviation, range, standard deviation. So we need to do the standard deviation for y minus x. And here's the key. You have to go through, standard deviations cannot just subtract like up above and do 10 minus 20. You have to go through the standard deviation of statistics. We're on page 112, by the way. So we have to go standard deviation of y or x, because we're going to be adding anyway. So of one of them squared plus, we'll talk about that in a second, standard deviation of the other one squared. Yeah, we don't have individual data, so we can't address outliers. Okay? So, no, you didn't have to. So let's keep calculating this. So this will be the square root of 20 squared plus 10 squared. And when you take the square root of that, that comes out to be 22.36 minutes. Now, I need to remind you of that little discussion. Even though we are subtracting and finding the difference in items, do you notice that this Pythagorean theorem does not have a minus sign in it? It has a plus. So I want to remind you of the little story that I told earlier in the year when I taught this to you. Let's say you have a cereal box, and it has a mean and a standard deviation, and we don't know how much is in it. And then we're going to pour some cereal out into a bowl, and it has a mean and a standard deviation, and we don't know how much is in it. So I'm not sure how much is in this box. I'm not sure how much I pour out of it. So am I more certain, or more uncertain, or less uncertain of what's left in the box? Well, how's my uncertainty? Is my certainty bigger or smaller? Bigger. I wasn't sure what I had to begin with. I wasn't sure what I poured out. So I am really, hence addition, really not sure what is left in the box. So even though I subtracted out cereal, I got a larger standard deviation. Yes. So, yes. So whether you add or subtract standard deviations, this is always a plus sign in here. Okay. All right. So we answered our three things: shape, center, and spread, and so that gets you an E. When I had done this my first time, I did the two formulas. I did the center and spread, and I had forgotten about to mention the shape. So anyway, hopefully you would catch that. All right, part B. Over the long run, what proportion of days will the train snake, that's X train, have to wait at Copperhead for the train from Diamondback to... So it's wondering, what proportion of days will the X train have to sit here and wait for this Y train to finish its path and get out of the way? So let's go over to what you guys told me this distribution looks like. You told me that the distribution of all of the Y's minus the X's are centered at 30 minutes. Because on average, Y takes 30 minutes longer. Okay? So I want to know when the X train will have to wait. And so, but I first need to start I need to first identify where they take the same amount of time. So what will this difference of Y minus X be if the trains take the same amount of time? 0. Well, since this is the placement of 30, my 0 will be over here. And so that's where the trains take the same amount of time. Take the same amount of time. All right. So along those lines, one of these ways, Y is bigger, Y takes longer, and one of those sides, X takes longer. Okay, so what's happening over here on this section to the right where the scores are positive? Y takes longer because Y minus X is positive. Y is taking longer. That means that X has to wait. Okay, and that's incidentally what this question is asking for. Question B says, what proportion of the days will have to wait? So this is what I am interested in finding, is how much area is this? So how can I identify how much area that is? Get a what? Get a p-value, or find out what this probability is there. Okay, so how do I find that area? What do I have to get right here? Z-score, and then norm CDF, that area up above it. All right, so how do I get that Z-score at that spot? Yep, X minus the mean over the standard deviation. X minus the mean over the standard deviation. Okay? And then I need to get that area above that. You do not have to write calculator speak, but I'm going up to positive 99, and that equals 0.91. I really don't like to just slop down a number, 0.91. So if you don't want to write the calculator speak, and you want to write something, here's another way. Probability that my X is greater than or equal to 0 is 0.91. Okay, you could just write that. So in other words, 91, and you don't have to write this out this way, but I'm doing this just so you really understand what this is saying. 91% of the days, what happens? Yep, the X train has to wait. That's a lot of days, and time is money. So maybe the Snake Gulch Railroad wants to not have the X train sitting there wasting time and money when they could be doing something else back at the station. So how long should the Snake Gulch Railroad delay the departure for train X so that the probability that it has to wait, or the proportion of days that it has to wait, is only 0.01. So where is the wait time on this picture here if I want it to only be 0.01? Where? Way up here. I want the amount of wait time to only be 0.01, not 0.91. So how can I get this z-score all the way up here and find out how much time it was from here to here. Aha, very good. So this z-score is going to be inverse norm of the area below is the z at that spot. And the inverse norm is 0.99 is 2.33. So if this is a z-score of 2.33, how do I know the time amount? That's the x value. Perfect. Plug it into our z-score formula, and we go 2.33 equals x minus the mean over the standard deviation. And if I solve that, x is 82.1 minutes. So see, the railway could be having the employees on that train back at the train station working 82.1 more minutes on something, okay, and not wasting their time. Yes? 0 for mean and 1 for standard deviation, always. Always. Because we always standardize it. When we do this z-score stuff, we are standardizing it. And so I never have y'all change the mean and standard deviation on the calculator because this work has to be shown for you to get full credit. So I just always make y'all show that and not mess with letting the calculator standardize it for you. Okay? All right, very good. So, in summary, what this problem had us do at first was that we could add those or subtracted those means like we normally thought, but the standard deviation had to go through the Pythagorean theorems, and it's always plussing, it's always adding, increasing this uncertainty, not ever subtracting right there. Okay. Now let's go on to the problem that you guys did last night for homework, which was on page 143. No, that's not right. Page 139 was the problem that y'all did last night. This was a problem number 6. I for real think that you should have been able to get 2 points and probably 3. The fourth one, I don't think I could have gotten it. It was just kind of one of those open-ended questions where I'm like, okay, what are you going for here? I have no idea, okay? But we're going to go through this, and I'm going to give you guys some strategies and such. By the way, the national average points on this in 2008 was 1.13 with a standard deviation of 1.04, okay? So that wasn't great. So let's see how you would have done. Here we go. Since this was homework and you're familiar with this problem, I'm just going to quick go through it. They took students that signed up for a magnet school. So all of these students that are in this study want to be in the magnet school. Okay. So so we're dealing with similar quality students. What kind of qualities would people be that sign up to go to magnet school? Okay, maybe smarter. How about more conscientious about studying? Ambitious, harder workers. How about parental support or home support and doing things? Okay, so we're not talking about comparing two different kinds of students. We take all the same kinds of students and they go through a lottery system where they randomly assign some of them to go to the magnet school and some of them go to the original school. Okay, this is true. That's truly how it works at in Fort Worth ISD. So anybody go to Alice Carden in that? I mean, I know y'all mostly went to Aledo, but that's an example where people try to get into that program. They also do. That's an elementary one that they try to get into. Okay, so here we go. Here is, they took this test at the magnet school. They did a post-test minus a pre-test, and you either have the list of data you can use, or they do give you the summary statistics right here for the magnet school. And so this is the average difference in the post minus pre-test scores for the magnet school. Then they give you the same data for the original school. Here's the individual scores for 12 students, and on average, here's what the score increase was with that standard deviation. So look at the first question. It says perform a test. That right there should be your clue to say, whoa, I've got to do a phantoms. So they're essentially telling you to do a full test. Okay? Now, the unfortunate thing is that this is a huge test to run. It takes a lot of time, and you just get 1 point for it. But this is a number 6, and a point's a point on a number 6, okay? Or on any of them. So budget your time. Pay attention to that. In the directions of the AP program, they will say you should allot 20 to 25 minutes for this problem number 6, okay? So be mindful of that and budget your time appropriately. Okay, so here, I did my parameters. This is 2 separate means because we had an average for the magnet group and an average for the original group. So this is the average post-test minus pre-test difference for students who attend the magnet school. And then the average post-test minus pre-test difference for students that attend the original school. For all such students that attend. That's your parameter. Your hypothesis statements right here on the left. The null hypothesis is that they are the same, and the alternative wondered if the average difference for the magnet school is better or higher than. So did the magnet school make them improve greater than the average for the original school? Okay, so P and H. Assumptions. I think I did not do all of my assumptions right. I know I just totally left out independence, by the way. So look at what I wrote for random. I don't like this either. It says random students from both populations stated to be randomly selected and assumed representative of their respective populations. That's what we used to say back in 2008. Maybe that would have been okay, but now what do they want you to say? Either what? Randomly selected or assigned. So in this case, is this considered an observational study where we randomly select from the population, or is this an experiment? What do you think this is? That was my first thought, but it is an experiment. And what is the treatment? The magnet school. So what they did was they took all similar kinds of students that applied. They did a lottery to randomly assign. So they used that lottery to randomly assign some of them to go to the magnet school and some of them to go to the original school. So this one. No. They took all the people that applied. Wait. Oh, I see what you're saying. Magnet school, you have to meet criteria, and then they send you there based on you meeting the criteria. Okay, maybe. Gotcha. See, so I agree that, technically in the public sector, we can't deny the people. So if they want to go to the magnet school, we have to allow them to go through the application process. So anyway, just blah, blah, blah. But that aside, here we go. Okay. So the point is, what I should have written here for random, let me fix it here. So for my random, I should have said all such students in this thing, all the ones that applied to go to the things are randomly assigned to magnet school or original school. Okay, and then I had even left off independent. It's like I knew I had to do my histograms, and I was so excited to do my histograms. I rushed to doing my histograms, and I really just totally left out independent. So anyway, so independent, what am I saying for that? 8 is less than 10% of all such magnet students. And then the other one was 12 is less than 10% of all such original studs. And since this is two groups, what am I also saying? That these two groups of students are independent of each other. Good. These two groups of students are independent of each other. Gosh, I doubt it. I mean, this is such a massive amount of stuff going into one point. I would hope that that little thing wasn't going to knock you off to a P, but I don't know. By the way, I forgot, I wanted to remind you that when you are doing your parameters, don't forget it's present tense. These are about students who attend the magnet school and who attend the original school, not attended, because that implies the sample, not the population, inferencing to the population. Okay, and then here we go with these samples were not large enough, so curse you. And we don't know that the populations were normally distributed, so that was our second line of defense. So curses, we have to now do this little histograms. And so make sure you label. So this was the difference in sign test for the magnet, number of students on the side. Difference in sign test for the original, number of students on the side. And see, I had really kind of made a dot plot. I just then transferred it into a histogram. Okay, so this is what you would be doing if you were doing it for real, and you could leave it as a dot. Now look at what they actually did on this is their ideal solution. So you can't tell this has a little line here in between the magnet and the original school, but it is showing two separate histograms here. Okay, they just did them side by side. So they fully expected this to be a condition that you satisfied in your information. Oh, I wanted to point out to you, let's see what they wrote. Starts right here. Because these graphs reveal no obvious departure from normality, it appears to be reasonable to proceed with a t-test. So that was their ideal solution. We write no outliers, no severe skew, somewhat symmetric for both things, and so nearly normal model applies. Okay? Yes. Is it sun? Somewhat symmetric. Like we never did it, but I established that. I was like, we should do sun. Somewhat symmetric, and then unimodal. Oh. Okay. Unimodal and no outliers. So this would be unimodal and no skew. Or wait. No, I guess not. That's what somewhat symmetric would say. Somewhat symmetric, unimodal, and no outliers. Nus, in this case. Sun. Okay. Yes? Yep. Okay, if you had a 0, then it goes to the right. Okay? If you have one that's on the line, it goes to the right. Okay, then you name it 2 sample t-test for means. Your t distribution, your degrees of freedom for t's you need to put. T-score was 2.487 on the degrees of freedom to 8.69. The p-value was 0.018. So less than 0.05. And that was actually part of the things. They specifically said you had to have your p-value connect linkage to alpha. So you specifically had to link to your alpha. Then we rejected the null hypothesis, and my conclusion was this. Since the p-value is less than alpha, I reject that the means are equal, and I have evidence that the mean of the magnet school difference is greater than the mean of the original school. Okay. Phew! All of that for 1 point. Okay, so anyway, so bide your time. Maybe you think that's not worth it, and you need to go spend it, and you can get more points if you spend more time on the other numbers 1 through 5. Okay? That's up to you. All right, but do keep in mind you'd need to get 2 points on the numbers 1 through 5 to make up for 1 point on this number 6. Okay? All right, but you know what? The next point is easier to get. This one says they give you the regression analysis for the magnet school, the computer printout for the magnet school, and the computer printout for the original school. And they ask you to state the equation and interpret the slope. That is factual, basic data that we learned how to do. That is not difficult. That is basic information that I taught you. So you should be able to look up here and get your coefficients right here. Your slope and your y-intercept for the magnet school. Your slope and your y-intercept for the original school. Don't forget that it is predicted post-test score. Don't forget your predicted hat. Okay, and then predicted original post-test, and then that. Let's talk about the interpret the slope. If you read that, interpret the slope, anybody want to snap? So for every 1 point increase in the pretest score, and you have a choice, you can either say the predicted y increases by 0.1811. You can say the predicted y increases by 0.181, or you can say the post-test increases about 0.1811. Use predicted or about. Don't use both. Predicted or about. Don't use both. Okay, and then the same thing for the original. So that should be a definite point that you get. Wasn't tough. It was basic facts that we did in this class. All right, next, moving on. So this one gives you then a null and alternative hypothesis about the slope. What test in our course have we learned that is a test about the slope? It is the one that we learned at the end, chapter 27. Linear regression t-test is a test about the slope. And so if I'm going to do a test about the slope, I should have a p-value for that. So look here, when they ask you the question, using the regression output, that's a clue. Okay? Use those kinds of clues when you take your test. They're giving you an indication of where to go. So we should be getting something from these two little regression outputs to tell me about the null and alternative hypothesis for slope. What do I use from these two? The p-value. Well, there's two of them. There's in this case, 0.078 and 0.706, which is the p-value that tells me about the slope. This one that is on the slope line. So the p-value for the magnet school's slope is 0.706. The p-value for the original school's slope is 0.0. So here is how those look for both of those. So I wrote it over here to the side. The magnet school has a p-value of that, so I fail to reject. So since the p-value is greater than alpha, we do not have evidence to reject the slope is 0. There's no caloric or no correlation between those. Second one, since the p-value is 0, which is less than alpha, I am rejecting it. And so, since p-value is less than alpha, we do have evidence to reject the beta is 0 and conclude that there is a linear correlation. Yes? No, so what happened, well, it'd probably get marked down to a P. So let's look and see. This is the third part. Okay, you get an E if both the p-value and both of the conclusions are correct. You get partially correct if 2 or 3 of the things are correct. So if you missed one p-value, or you missed the 2 p-values, but then you made correct conclusions from those wrong p-values, that would give you partial credit. So if you put the p-value down wrong, but your conclusion was connected to that properly. Okay? All right. Now, this last point goes for part D. I don't think I would have gotten it. I mean, let's just kind of look at the question. Let's look at how broad this question. Okay, look here. What additional information do the regression analyses give the student give on the student performance on the science test at the two schools beyond the comparison of the average differences in Part A? So I'm like, I mean, just throw a dart anywhere in the dark with the blindfold on, okay? So, okay. But here's what they were going for. If this is, and I see it once they say it in the grading guidelines, okay? It's easy to see what they're saying, but look here, this is interesting. Let's look at the original school. Let's see how the students did in the original school, post and pre. Do you see these people here? Do you see how they did low on the pre-test? And how did they also do on the post-test? Low. So students did low on the pre-test, also did low on the post-test. Okay? How about over here? These students at the other school that did high on the pre-test, how did they also do on the post-test? High. So at the original school, they pretty much performed low pre, low post, high pre, high post. And so I wrote this. The original school students only performed well on the post test if they had also done well on the pre-test. So in essence, did the schooling make a bit much of a difference to their performance? Not really. But let's look at the magnet school. Look at this magnet school data. Okay? So what we would say here, while that gave us pretty much no slope, it's interesting what it tells us. Look at these students who had low pre-test scores. How did they do on the post? High. And then look at these students that had high pre-test scores. How did they do on the post-test? High. So essentially, you've got all of these scores in this area. So what this says is, regardless of how the magnet students did before the schooling, low or high, they all got a higher post-test score. So isn't that interesting? That having no slope actually kind of said that the magnet school worked. I thought that was interesting. So you can see from the magnet school that students score high on the post-test regardless of their pre-test score. That's what they wanted you to see. That's what they were going for. But isn't that so interesting? Because I don't know, my brain kind of is trained to say, oh, if I have a slope, then that's like a good thing, right? Because I was supposed to say there was a relationship between them. And anyway, so there's just some different things on that I could talk about forever, and I'm not going to anymore. Okay. That is the end of those. So hopefully you grasped some new strategies there. How many of you got at least 1 point on that?